In this video, we're going to discuss the first sample problem for electrochemical cells. Now let us read the problem. Consider the voltaic cell. We have 3 moles of silver solid plus nitrate ion plus 4 moles of hydrogen ion forming 3 silver ions plus nitrogen monoxide plus 2 moles of water at 25 degrees Celsius. So we are given with the following quantities as N, which is the number of moles that canceled out during the redox reaction occurs for this one as 3 moles. So you're not going to solve this. We are already given with this. And then we are given with the further quantities values as the redox cell with a voltage of 0.964 volts and the voltage for the oxidation cell at negative 0.799 volts, and our Faraday's constant is 9.648 times 10 raised to 4 joule per mole volts. Now, our gas constant for SI unit is 8.314 joule per mole Kelvin. Now, for letter A, we're going to solve for delta G naught, or the free energies, and for letter B, we're going to solve for the reaction constant K. Now let's proceed with the solution. For the standard voltage, we need to first determine this quantity so that we can solve for the delta G naught since we are not given with the standard voltage. So the standard voltage is equal to the sum of the voltage at the reduction cell plus the voltage at the oxidation cell. So we're going to add zero point 0.6 or 0.964 volts plus negative 0.799 volts gives us 0.165 volts. And for the Gibbs free energy, delta G naught is equal to negative N multiplied with the Faraday's constant times E naught, the standard voltage. Okay. Now let's substitute the following values as negative 3 moles times the Faraday's constant at 9.648 times 10 raised to 4 joule per mole volts times the solved standard voltage at 0.165 volts. This gives us the product of 47 or negative 47,757.6 joules. Okay? So this is the answer for unknown letter A. The Gibbs free energy delta G naught is equal to negative 48,000 joules. Now let's proceed with the reaction constants. Okay. So since we are given with the temperature at 25 degrees Celsius, we can use still this equation as the standard voltage is equal to the gas constant times temperature at Kelvin. Okay, so the 25 degrees Celsius must be converted to Kelvin. Multiply it with the natural logarithm K all over the number of electrons that canceled out for this reaction. Multiply it with the Faraday's constant. Now let's derive our reaction constant. If we're going to derive our reaction constant, we need to cross multiply into this side equation N and F. So E naught multiplied with N times F and then divide it with the gas constants and temperature R and T. So this gives us the natural logarithm of K multiplied with E naught times N times F all over RT. To bring out K, we need to use antilog for both sides of equation. This gives us with this new conformation of equation, K is equal to epsilon is raised to the following quantity, E naught multiplied with N times F all over R times T. If we're going to substitute the following values, epsilon is raised to, our E naught is 0.165 volts times 3 moles times our Faraday constant 9.648 times 10 raised to 4 joule per mole times volts all over our gas constant 8.314 joule per mole Kelvin times our temperature, which is converted to Kelvin. If we're going to convert degrees Celsius to Kelvin, you're going to add 273.15. So 25 plus 20, 273.15 kelvins. Now, this gives us with an answer of 232935181.5. So this is unitless. Okay? Or 232,935,181.5. So this is unitless. So another version for this solution, since the problem is at 25 degrees Celsius, okay? So we're going to use this one. K now is equal to epsilon raised to E naught multiplied with N all over 0.00257. Okay, now substitute the following values. 0.165 times 3 moles all over 0.0257 volts. This gives us with the final answer, which is the same as the other one. 233 million, which is also unitless. Now, our next video is a second problem for electrochemical cells.